welcome to BCIS 3347 Data Communications. Today we're going to be talking about Chapter 3, and if you want to follow along at home and you want to see the slides, you can click on that link right there, and that will open up a link to my shared Google folder that has all the slides. As I do these videos, I create transcripts as well, so if you want to look through those, you're certainly free to. I've already opened up the slides right here so that I can go ahead and full screen it and present it. And like I said, today is Chapter 3, Transmission Basics and Networking Media. So let's go ahead and hop on in here. Okay, so Transmission Basics and Networking Media. So the objectives for this chapter are to talk about the basic data transmission concepts, so just the basic concepts of what it takes to get data from point A to point B. We'll talk about duplexing, half duplexing, full duplexing, etc. We'll talk about attenuation, latency, noise. We're going to talk about some of the different types of media, STP, UTP, fiber optic, etc. We're going to compare the benefits and limitations of some of those different media. When is it appropriate to pick one over another? We'll talk about some of the principles behind and uses for serial cables. We'll talk about wiring standards and some of the best practices for cabling buildings and work areas. So when we talk about transmitting data, we're talking about the issues related to signals along some sort of a network medium. Those mediums can be copper, which tends to be the most common. Wireless is probably the other most common type of media. So it can be through the airways, it can be via copper, it can be via some sort of fiber optic or light-based medium. So there's several different ways to go about transmitting signals. When we talk about transmission is that actual process of transmitting that data, and so it describes that whole process. A transceiver is a dual device. It's a device that both allows you to transmit and receive. Typically, you've got to have a transmitter on one end to actually send out a signal, and then on the other end, you have to have a device that receives it. And that's fine if you have one-way communication, but in reality, we really want two-way communication most of the time. And when that's the case, we need some sort of transceiver, a device that's both able to transmit as well as receive. So some of the issues related to analog and digital signaling that are important, things like whether or not it's an analog or digital signal. The signaling that is used for both is a little bit different, and so we'll talk about those in the next few slides. Some of the different characteristics that you need to be aware of before we get into this. The voltage, it's basically the pressure, if you will, or electrical pressure, if you will. Electrical signal strength, so it's directly proportional to the voltage, and so the higher the voltage, the stronger the signal. And then lastly, signals, current, light pulses, electromagnetic waves. It's the thing that represents the 1 and the 0, or the on and the off, or whatever, at least when we're talking about digital. Okay, so analog and data signals. With an analog signal, the voltage is going to vary continuously, so it's going to look like a wave, and that wave can take on different shapes, but there's going to be ups and downs, there's going to be peaks and troughs, and we'll see an example here in just a second. But some of the fundamental properties or characteristics of these waves are their amplitude, their frequency, wavelength, and phase. So all waves are going to have these characteristics about them, and we'll talk about those, like I said, a little bit more here. So when we talk about the amplitude, it's how high does that wave go? The higher the amplitude, the stronger the signal. Remember, we talked about that just a second ago. We also have the frequency. What's the frequency? The frequency is the time that's required for the wave to make one complete loop. So it's a frequency. How often does it do it? If you think about waves in the ocean, how often do those waves come in over a fixed period of time? Here we're talking about the phase of a wave. When we're talking about phase, we're not actually talking about an individual signal, an individual wave. When we're talking about phase, we're talking about the comparison of two or more waves. And in this case, we've got two waves. They're in this case, they're 90 degrees out of phase. So we can see this particular one. It makes one full cycle, This one is exactly 90 degrees past. If that's a full cycle, what's the cycle? 360 degrees. It's the opportunity to go all the way around, so 360 degrees. Well, in this particular case, it starts 90 degrees out of phase, this red wave does. So it's said to be 90 degrees out of phase. So again, phase refers to a comparison between two or more signals. As far as the benefits, of analog over digital, remember we're talking about two different kinds of signals. They're both capable of carrying information. Neither one is inherently better than the other. Each one has certain characteristics that make it better in certain situations. In this particular case, analog is not always inferior to digital. Digital does have some benefits, but so does analog. In this case, analog is able to convey greater subtleties with less energy. It doesn't cost as much to be able to represent small little minute differences. But a drawback of analog signals is that varied and imprecise voltage. It makes it susceptible to transmission flaws. So sometimes those differences are so small, it's very hard to tell the difference sometimes. Digital signals are different in that rather than having that wave to represent differences in information that's being carried on that wave, we pretty much have an on or off situation. Positive voltage represents a 1, zero voltage represents a 0. So if there's some voltage on the line, we're representing 1s. If there's no voltage, we're representing 0s. So it's much easier to determine what the data actually is. So here's an example of our signal. So we have a signal that's giving us 1, 0, 1, 0, 1, 0, 1 in this case. So it's repeating, at least over these bits, those particular numbers. So it's pretty obvious. If there's voltage on the line, it's a 1. If we turn the voltage off, it's a 0, back and forth. Now, how does this represent information? Well, if we apply some sort of protocol to it, we say that every 8 bits is going to represent a byte. We can start to represent things. If we can only represent on or off, that doesn't tell us much. But if we can combine those together in the form of bytes, now all of a sudden we can start to represent things. We can represent much larger numbers. We can represent various letters of the alphabet. And that's kind of what they're starting to get at down here. So if we've got 8 bits, which is a byte, 0 through 7, we can actually represent 256 different numbers, 256 different characters. You could reference this to the ASCII table and be able to pick out specific numbers or letters that a particular byte might represent. So it's actually 128 plus 64 plus 32. So when you add all those up, you'll end up with 0 through 255, 256 different combinations. Okay, some people think it's important to be able to convert back and forth between decimal and to base 10, all that kind of stuff, and I think there is some value there. I don't know that you really have to spend a lot of time, especially not in this class, but if you really want to, you can pull up the calculator there, and in this case we're in decimal already, so let's say we want to represent 255. Why 255? Let's go look and see what it looks like in binary. Nope, it's 8 bits, and they're all 1s. If we wanted to represent, let's clear this, and let's say 1, 1, 0, 1, 0, 1, 1, 1. What does that represent in decimal? I'll switch over and it's 215. So it's a pretty easy way to go back and forth between some of those different numbers. So you can do these calculations by hand, or you can simply use the calculator. Use the calculator, it's easier. Okay, so we talked about some of the advantages of analog over digital, but digital has some benefits over analog as well. Digital tends to be more reliable. It's easier to figure out what the signal is, when there's positives, when there's no voltage. So we can tell those 1s and 0s a little bit more easily. It's also less susceptible to noise interference. So those are a couple of the advantages. Some of the weaknesses, or one of the weaknesses of digital signals, is it takes a lot of pulses to be able to transmit the same amount of information. So we have to be able to transmit a lot of 1s and 0s to be able to represent that same kind of information that we could actually receive with an analog signal. There's also overhead associated with digital signals. In other words, we have to have some sort of mechanism in place that says those 8 bits actually represent this particular number or this particular letter. So we have to tack on some additional information to say, okay, these 8 bits got there, they got there in one piece. The ones and zeros that are there are actually the ones that were transmitted. So this comes in the form of overhead. So how does it actually represent data? How do we manipulate the signal to be able to actually represent something? Well, we do it through some sort of modulation. We're going to modify the signal in order to be able to make it create information. If we send out the same signal the whole time, it doesn't mean anything. If all we do is send out ones over and over and over again, it doesn't tell us anything. It doesn't allow us to communicate anything. But if we modulate that signal back and forth, now all of a sudden we can start to code information into it. And that's where modulation comes into play. Network connection may handle only analog signals. Modem actually stands for modulate, demodulate. So these are 2 devices on each end, or a device on each end. And it allows you to, say for example, on one end, it allows you to take a digital signal that's going to come from a computer, convert it into an analog signal to be transmitted across an analog circuit, and then be received on the other end by another modem and converted back into a digital signal so that the computer on the other end can understand that. As far as data modulation, it's a technology modifying analog signals and makes the data suitable for carrying over a communication path. So that's basically what I just got through talking about. In the analog world, we're talking about needing to send some sort of signal along with our actual data, and this is where the idea of a carrier wave comes into play. If we're going to transmit at a particular frequency with a particular amplitude, as it cycles, it goes up and down, it goes up and down, and on the receiving side, that's what it's supposed to receive. But that's just the signal itself. The signal itself doesn't tell us anything. Again, it's the same thing as broadcasting all ones or all zeros. It doesn't tell us anything. So we've got to do something a little bit different to that signal in order to make it represent the data that we're trying to send along with it. So what we do is we end up adding on top of the carrier wave an information wave. We manipulate the carrier wave a little bit. We add an information wave to it, which modifies that carrier wave. On the receiving end, it looks at the difference of what it's expecting for the carrier wave and is able to determine what the information trying to be conveyed is. So that's how transmitting data via analog signals works. We can modulate that signal in several different ways. We can do it with frequency modulation, FM, amplitude modulation, AM, or and then DSL does their own thing. I'll talk about that a little bit later. For FM modulation, this is the same thing you see on your radio. FM modulation, we're modulating the frequency up and down. So we will increase the frequency, or not up and down, the wave that goes from right to left over time. We will modulate that back and forth. So we expect to see a certain frequency, and the difference between that frequency and what was actually broadcast tells us what the signal is that's supposed to be there, what the information signal is. Amplitude modulation is the same thing, except it's the up and down part. If we expect it to come in at a certain amplitude and it actually comes in at more or less, that tells us the difference. The difference is our actual signal that we're trying to, or actual information that we're trying to communicate. So here's kind of an example of what we might be talking about. So we have our carrier wave. This is our amplitude. This is our frequency. So if we expect our frequency, we expect our wave to complete right here. If we come straight down here and we see, wait a minute, we've actually got 2 waves in the same amount of time. We really expected to see 1. The difference between these 2 is our information right here. And so on the receiving side, it's able to be able to strip this out and say, oh, this is the information you're actually trying to transmit. Okay, so as far as transmitting stuff, we basically have several different approaches that we can take. In the very early days, we had simplex. More recently, half duplex. Now, for the most part, we tend to use full duplex in the vast majority of situations. Simplex, the signal travels in one direction. That's the only direction it can travel, and it's a very simplistic approach to doing things. You don't really see that anymore. But in the very early days, when channels were very expensive to create, you didn't have a lot of people that had the ability to transmit or receive. This was an approach that was used. Half duplex can send data in both directions, but only one at a time. An example of this might be, for example, CB radios. One person can transmit while another person listens. When that person speaking is done, they let the trigger go on the transmitter, and the other person can speak. Telephones used to be this way not all that long ago. Both people could not be talking at the same time. So that's an example of half duplex transmission. They use the same communication medium, it's just you can't both be on it at the same time. Full duplex allows you to go in both directions at the same time. And that's pretty much how a conversation works today. If you're talking to somebody, both people can be talking at the same time. It doesn't necessarily mean you can understand each other, but it's something that you can do. And when you're talking about data, it can be useful because it allows you to send data up and down at the same time. So, for example, if you access a website, you can both be requesting a website with one tab on your browser and downloading something on another tab. So it becomes very convenient that way. So it's kind of a graphical representation of what we just got through talking about. Something else you need to be aware of is this concept of channel. It's a distinct communication path between nodes, and they can be separated either physically or logically. In other words, we can have physical separate data paths for data to be able to go through, or it can be logical. In other words, we can have multiple channels within a single physical data path. The advantage to full duplex it is an increase in speed of the data. Some modems and network interface cards allow for specifying half or full duplex communication, but most of them use full duplex by default anymore. So, now what happens if we have lots of devices or several devices that want to use the same communication channel at the same time? Well, that's where multiplexing comes in. It allows multiple signals to travel simultaneously over one medium. You might do this, say, for example, when you have a long distance channel that you need to be able to send data through. On one end, let's say you've got an office in New York and an office in Los Angeles. That communications channel is very expensive, but you may have multiple systems in New York that want to talk to multiple systems in Los Angeles. You can either have multiple channels, which gets very expensive, or through a form of multiplexing, you can share that one communication medium to be able to do that. Multiplexing basically breaks things up in terms of subchannels. You have a multiplexer, you have a demultiplexer. So those subchannels are logical, multiple smaller channels. So those are individual subchannels that you have. The multiplexer is a device that combines all on one side that combines all those channel signals, and then on the other end, you need to be able to break those signals back out to the individual systems that they need to go to. So there's several different ways that we can do that. One of these is called time division multiplexing. And that basically says, okay, for this particular communication medium, let's say this one right here is a cable. For this particular communication medium, we've got 3 computers in New York. We've got 3 computers in Los Angeles that all need to be able to talk to each other. What we're going to do is, for the first 2 time slots, we're going to allow computer A to talk. So we're going to send our message in those first 2 time slots. The next 2 time slots are going to allow computer B to talk, and then C, and then we're going to just cycle through that over and over again until on the receiving end they receive them in the order that they're supposed to. So our multiplexer is going to break those signals, take those signals from our sending side, combine them so that they can be transmitted across our common communication line, and then our demultiplexer is going to to take that single signal coming in, break them back apart to their destination nodes. Does that make sense? That's just one way of doing it. There's a variety of different ways. There's statistical multiplexing. And the details of it, I think, are really kind of beyond the scope of this class. But the idea is that with statistical multiplexing, there are other ways to break up the data to make more efficient use of the line. And statistical multiplexing is a much more efficient approach. Frequency division multiplexing involves the use of fiber optic channel or fiber optic cable, and again allows you to break up. Actually, I shouldn't say that. It breaks it up based on the frequency, so you can actually have multiple signals traveling down your communication line at the same time. They're just using specific parts of the cabling for it. And then you have wavelength division multiplexing, which is what I was talking about just a second ago. Uses fiber optic to be able to use a single communications medium for multiple signals. Then dense wavelength division multiplexing, again, just another way of being able to do that. Something else we need to know when we're talking about these different channels and how to connect different devices is this idea of the relationship between the different nodes. And this is something you'll see in most networking texts. We have point-to-point, point-to-multipoint, broadcast, non-broadcast. When we talk about point-to-point, we're talking about from one location to the next, to a specific location. So we're not talking about one computer to many computers. We're talking about one computer to one computer. Usually this is the case when we're trying to link up two different buildings. You may be trying to link up two different locations, New York and Los Angeles, for example. But we're trying to link up those two specific things. So one transmitter, one receiver, or maybe one transceiver on one end and one transceiver on the other end, more likely. We've also got point-to-multipoint transmission. This is what you see a lot of times in your office space, for example. So you may have a server in your office, but then you've got multiple receivers, multiple clients in that office that are going to access that single server. So you've got a point-to-multipoint transmission. A lot of times what you'll actually see is a combination of these different relationships between nodes. So you may have a point-to-multipoint within a specific office building, but then a point-to-point relationship between that office building and another office building, serving as their backbone. You've also got broadcast transmission, where one transmitter and multiple undefined receivers. Think of radio, for example. They're sending out a signal, but they really don't care about who receives it. They may have one person really paying attention and listening. Then again, they may have thousands or hundreds of thousands of people receiving. So you really don't have any control over who's actually receiving. This is as opposed to non-broadcast, where we're talking about one transmitter and multiple defined recipients. So specific people, we're going to allow lots of people to access it, but we're going to know specifically who they are and control access to it. So again, with point-to-point, we may be linking up two different buildings, Los Angeles and New York. With broadcast, we're going to send out a TV signal or a radio signal, and all the homes in the area are going to be able to pick it up. They may be watching, they might be watching something else, or not watching TV at all. This is you guys, you should be studying right now, so you're not watching TV, so and so on. So that's kind of how broadcast transmissions work. So how much data can we send? Well, that's a good question. Depends on the medium. There's lots of factors that affect this. We're going to measure it by looking at the throughput. We're going to measure it by looking at the bandwidth. So throughput is the amount of data transmitted during a given time period. It's also called capacity or bandwidth, and it's expressed as bits transmitted per second. That's fine for the most part. Bandwidth, though, is another measure, if you will. It's the difference between the highest and lowest frequencies that the medium can transmit. It's a range of frequencies, and it's measured in hertz. You really want to know about throughput. It is what you really kind of want to focus on, because it's what actually tells you how much of your data is going through without respect to the overhead that's on top of that. So as far as the throughput measures, again, we're going to measure it in bits per second. 1 bit per second is obviously extremely slow. even kilobits per second, but 1,000 bits per second is a kilo, 1 kilobit per second, kbps. Megabits per second, now we're starting to talk a little bit. Gigabits per second is great. If you get up to terabits per second, you're living life really well. Now, what's the difference between baseband versus broadband? Baseband are where digital signals are sent through direct current pulses applied to the wire. It's going to reserve that wire. It's going to use all of the capacity of that wire. It's not going to share any of the capacity with anything else. You can send one signal at a time. That's all it can be used for. Ethernet's an example of that. Broadband transmissions, however, they're going to use signals modulated as RF frequencies along analog waves, but it's going to use different frequency ranges. It's going to allow you to send multiple signals down that same wire at the same time. So, for example, think about your cable TV. A lot of people are getting the signals for their internet across it, but they're also getting the signals for their television service across it. So you're able to use use it for multiple transmission types. Pretty much every type of transmission medium is subject to some sort of transmission flaws. Some are more susceptible to others. And when we talk about those can come largely tend to be described as some sort of noise. So noise is just any kind of undesirable influence that degrades or distorts the signal. Those ones and zeros that we're trying to represent, if you get a little bit of noise, all of a sudden one of those ones becomes a zero, or one of those zeros becomes a one. And when we're trying to represent data, we're trying to represent numbers or characters, that becomes problematic. Some general categories of noise: electromagnetic interference, crosstalk are a couple of examples. EMI, electromagnetic interference, can come if, for example, you're too close to another transmitter, you're close to electrical lines or something like that. Those can cause problems with the signals that are going through your transmission medium. Crosstalk is sometimes when you have data cables that are running too close to each other and the shielding is not very good on them, that sometimes the data being transmitted on one wire can actually be picked up on an adjacent wire. So that can become a problem. So here's kind of an example. If we're looking at the end of a wire, so to speak, we've cut it and we're kind of looking at it, we've got our wire sheathing right here. And then inside of that wire sheathing, we've got individual wires. Well, if we've got maybe a crack in some of the insulation or something like that, one of our wires' signal may actually affect the other wires, and those other wires may actually pick it up. Attenuation can be another problem. Attenuation refers to the loss of the signal strength as it gets further away from the source. So the further it gets away, the weaker that signal is going to become. Think about trying to yell across a football field. The further away you get, if you're, one person's at the 10-yard line and the next person's at the 20-yard line, you can probably speak fairly normally and hear that person just fine. But again, if you're at the 10-yard line and that other person's at the 50, they're significantly further. You might have to raise your voice. If you're at the 10-yard line and they're all the way at the other end of the field, you're probably going to have to yell for them to be able to hear you. So this is attenuation. You're losing signal as that person gets further away from you. As far as boosting signals, there's several different approaches. It really sort of depends on what you're doing. If you've got an analog signal that you're using, you have to actually amplify it. Now, the downside and this is one of the downsides to analog signals, is when you're going to amplify it, if you go to amplify it, any noise that's been picked up along the way is just going to be amplified. So again, let's go back to our football field, and person's at the 10-yard line and the other person's at the other end of the stadium. Now let's fill the stands full of screaming fans. If the person at the 10-yard line is yelling to the other person, and you've got all that background noise, you go to amplify it, what's going to happen? You amplify not only that person that's at the 10-yard line trying to communicate it, but you also amplify all that crowd noise as well. So that's the problem with analog signals. Digital signals, on the other hand, you're actually able to do, it's a similar process, but instead of amplifying, it's called regeneration, or repeaters. So when you regenerate a digital signal, what's going to happen is everything is going to be restored back to the way it was when that signal was originally created. And so that's kind of the difference between a repeater versus an amplifier. Amplifiers and repeaters both operate at the physical layer of the OSI model. So here's kind of an example of these two in action. So with our analog signal, we've got a signal that's doing fine to start out with, and it starts to get introduced to a little bit of noise right here. There's a transmitting tower. It starts to degrade the signal just a little bit here. It's not quite as nice and smooth as it was before the interference. When we get to the amplifier, it starts to boost the signal again, but it's boosting that noise along with it. So that's not a desirable trait. As opposed to analog, we have our zeros and ones, etc. We get a little bit of noise, and now all of a sudden it doesn't look quite so good. We go through a repeater, it's going to regenerate that original signal. As long as that noise isn't too severe that we actually flip a bit or anything, it goes back to being a nice crisp signal. Another characteristic related to transmission flaws is this concept of latency, delay between signal transmission and receipt. It's not usually a big deal for a local area network because you're close, but as you get further and further away, the delay between signals tends to become more noticeable, and this is referred to as latency. So if you end up with, say, a switch or a router that becomes very congested because of the amount of work that it's doing, it's low on memory, things like that, it can increase the latency and slow things down. Some of the causes of latency are cable length. The longer they are, not only do you have that attenuation issue, you also tend to increase the likelihood of latency. And then intervening connectivity device. Round trip time is also another contributing factor to latency. It's the time for the packet to go from the sender to the receiver and then back again from the receiver to the sender. So when you send in a request to a web page, you type in www.google.com, for example, round trip time refers to the time that it takes for your request to go out of your local network through the router, out to DNS servers, finding the servers, getting directed to the IP address of Google, and then coming back, returning that web page back to you. And so that round trip time, so the amount of time that it takes you to get from your machine to Google, you can essentially double that. And that represents your round trip time. Let's see, common media characteristics. Selecting transmission media, you need to match the networking needs with the media characteristics. There's lots of different types of media that are available. We tend to standardize on just a few, and we'll talk about those here in just a second. But there are different characteristics, and there's different reasons to pick different types of media depending on your situation. Some of those characteristics you probably want to consider, things like throughput, cost, noise immunity, size and scalability, and then the connectors and media converters. So these next several slides talk about each one of these in more detail. Throughput's generally a pretty big factor. We want to make sure that we can process the data that we need to process. If you're just sending text files back and forth or email without attachments, it's not usually a big deal. But if you're sending large files, big files, music and videos and digital images and stuff like that, all of a sudden throughput can become a bigger deal. So you need to be aware of what kind of data you're going to be using, going to be sending across your network before picking a particular medium. Some of the causes of throughput limitations, the laws of physics. I mean, certain mediums are able to transmit more than others. So that's why there's different standards for unshielded twisted pair, for example. Some can transmit up to 10 gigabit ranges. Others are restricted to 10 megabit. So lots of differences in between. Signaling and multiplexing techniques, noise, devices connected to the transmission medium, etc. When it comes to throughput, fiber optic cables are really kind of the king of this area. If throughput is heads and shoulders above everything else, your primary need, you probably want to settle on fiber optic cable. This is assuming cost is not as big a deal, because cost is more significant when it comes to fiber optic. But if throughput is your maximum, is your primary concern, and significantly outweighs cost concerns, fiber optic is the way to go. As far as cost, Sometimes it's kind of hard to figure out. It's so hard to determine cost because when we talk about our network media, um, the longevity, the life of it, tends to outlive a lot of the other components in our network infrastructure. Uh, as far as some of the dependencies, the cost, immediate cost dependencies, what existing hardware do you have? How big is the network? How much does labor cost, which is different from the area of the country that you might be in? Variables influencing final cost. The installation, depending on where you are, you probably spend anywhere, somewhere around $100 per drop. So you talk about a small company with 50 drops, that cost can start to add up pretty quick. New infrastructure cost versus reuse. So how often do you have to replace switches and routers and the wiring that goes with that? Maintenance and support costs. You need to move a drop, you need to add drops. Um, you have a drop that's not functioning properly, you got to support that. Cost of lower transmission rate affecting productivity. You've got a network infrastructure that's designed to send data at 10 megabit. Well, that was fine 15 years ago. Today, that's going to negatively affect productivity in most cases. The cost of downtime. It's not the same from one company to the next. For some, they have plenty of things to be doing. If the network goes down for a little bit, it may not affect them. For others, say Amazon, for example, whose entire livelihood is online, if they go down, the cost is significant. And then there's the cost of obsolescence, stuff just getting old. There's noise immunity too. Not all these different mediums are as susceptible to noise as others are. So noise distorts the signals. We were already talking about that earlier. The distortion rate is dependent upon the transmission medium. Fiber optic is least susceptible to noise. In other words, electromagnetic interference doesn't affect fiber optic signals. They're using light. So fiber optic tends to be very good at being immune to noise. Some of the things that you can do to try to limit the impact of noise on your network, make sure that the cabling's installed appropriately. Make sure that you're not running cables parallel to electrical cables, for example. You can select media protecting signal from the noise. So, for example, instead of going with unshielded twisted pair, which is the most common type of cabling, maybe you need shielded twisted pair. It tends to have a better shielding that helps protect it from signals. And then anti-noise algorithms as well. Another consideration is size and scalability. Some of the things you need to think about are the number of nodes per segment, the maximum length of a segment, the maximum network length. So those are all things you need to start to think about when you're designing your network. And we're talking about network design here. Maximum nodes per network segment dependency, you have to think about attenuation and latency. The further those nodes are away from their server, for example, or their point of demarcation, the router their gateway that gets out to the internet, the more latency there's going to be, the more attenuation that there's going to be, and then the maximum segment length dependency. Another consideration: size and scalability. The segment types. How populated or unpopulated are there? How many nodes are there on a particular segment? If you've got lots of nodes on a particular segment, you're going to tend to have a lot more what's referred to as a domain collision, where too many nodes are trying to talk at the same time. This requires retransmissions to occur, which takes up more of the bandwidth from your segment, so it can create a problem. If it's less populated, it's going to be less of a problem. And then segment length limitation. After a certain distance, signal losses, the signal loses strength, so you can't really accurately send and transmit. Other issues are the connectors that are going to be used. That's one of the things you have to think about is physically how are you going to connect your cabling to your various devices. You have to think that through so that you make sure that if you're using unshielded twisted pair with RJ45 connectors, you didn't buy a bunch of network cards that use BNC connectors. So it's something you have to be consistent with throughout your network. It impacts your hardware, your media, as well as the hardware choices that you make, and affects the cost. RJ45 connectors are pretty cheap. BNC are going to cost more. You can convert, but again, you're going to end up increasing some of your costs that way. Here's a card, for example, that allows you to convert from to and from copper RJ45 connectors to fiber optic. Coax is another medium that has been used in the past. It's not nearly as common or popular today, but it is out there. It is a choice. It looks very similar to the kind of cabling that you'll see in your house for cable television. Typically in industrial environments or commercial environments, it's a thicker type of cable, though. Tends to do very well as far as electromagnetic interference and all that kind of stuff. The shielding that it has is significantly more substantial than what you see on unshielded twisted pair, or even just shielded twisted pair for that matter. But it has some pretty good throughput. So it's highly noise resistant and has advantages over twisted pair cabling. It does have disadvantages too. It costs more. It's also more difficult to work with. It doesn't bend as easily. Hard to make corners and stuff like that. And there's lots of different specifications, so that not all cabling is the same. Some of the basic data usage cables that you'll see are G6, 8, 58, and 59. And there's an example of what that cable might look like in terms of the connectors. So it's a F-type connector and a BNC type connector. Twisted pair is by far the most common type of cabling that you tend to see. There's a couple of different kinds. There's twisted pair, or excuse me, unshielded twisted pair and shielded twisted pair, or UTP, STP, respectively. And essentially, this is kind of what it's going to look like. You've got 8 conductors, so 4 pairs of wires, and they're encased in some sort of a sheath to help protect them. Some of those characteristics we talked about earlier, the physical or the physics behind it. By twisting the cabling, it allows us to reduce the effects of interference. It allows us to transmit our signals further. So the more twists per foot, the better the cabling is going to be, and it tends to cost more. So that's one of the downsides to it. But it's what allows us to get up to those gigabit and even 10 gigabit speeds. Twist ratio, twist per meter foot, high twist rate ratio, greater attenuation. There's lots of different designs in terms of the twist ratio, number of pair of wires, the quality of the copper that's used, the quality of the shielding, etc., etc. In some cases, for regular UTP type cable or shielded twisted pair type cable, we're used to seeing 4 pairs of wires, but you can buy many, many, many more pairs of wires for larger, more commercial or industrial environments. There's a couple of different wiring standards, in other words, the pinouts, if you will. We'll see another slide on that here in just a second, that tell you where these wires should actually go. So let's switch over here in just a second. Shows it. So I'll come back to that here in just a second. Most common twisted pair types, categories 3, 5, 5E, 6, 6A, 7 in class. I do not want to see anything less than 5E and probably nothing less than 6. These are really more phone grade, and if we're talking about 10 megabit networks, 5 may be fine, but I mean, we really should be focusing on higher level cat cables. The advantages of twisted pair, it's really pretty, it's one of the cheaper alternatives, and it works extremely well. It's very flexible, easy installation. You can get pretty good distances with it without requiring a repeater, and it accommodates several different topologies. A couple of different categories. We've talked about this just briefly, STP and UTP. For the most part, everybody's going to use UTP. It costs less and is easy to work with. STP is a little bit more difficult to work with. The shielding is a little bit thicker. But if you're in an environment that has a lot of electrical devices, motors, and things like that, it can be a good alternative. It's still relatively inexpensive compared to some of the other choices, but it works extremely well. As far as what it might look like, you've got the shielding here. If it's a shielded STP, you may have something like this, some additional foil or some kind of sheathing to help protect it. Your individual wires are going to be protected themselves, and then there's the copper conductor itself. You're going to notice the color codes. There are color codes. We'll talk about that a little bit more here in a little bit, but those are important. They mean something. They have to go to a specific place on the connector. So there's an actual picture of one of the cablings, or one of the cables, and you can see the twists in the wires. So as far as the ability to transmit data, you're really not going to see any difference unless you're subject to interference, in which case STP is going to do better because you're not going to have as many collisions and having to retransmit or anything like that. The costs are fairly comparable. STP does cost more in general, but it's not usually a lot more. So unless there's a real need, UTP usually works just fine. But if you have a need, it's not going to break the bank to go ahead and step up to shielded twisted pair. They both use RJ45 jacks. These look very similar to the old telephone jacks that you used to see, if anybody's familiar with those anymore, that are just two pair basically. Those are RJ11 jacks, but you really don't see those hardly at all anymore. STP is more noise resistant, which we've already talked about, and the maximum segment length does not change from one to the next. They're both about 100 meters. Now, related to this idea of twisted pair are this concept of patch cables. You see these a lot, especially in server rooms, where you've got little short cable runs that you need. You need to be able to run from a switch to a router, or from a switch to a server, or something like that. And these are referred to as patch cables. They're connectors at both ends, and they're relatively short. Something else you need to be concerned with is this idea of proper cable termination. Regardless of the type of cabling that you're talking about, you need to properly terminate the cables. If you don't, you're setting yourself up for being more susceptible to interference and things like that. If you're lucky. If you're not lucky, it won't work at all. Poor termination leads to loss or noise. As far as termination with respect to UTP or STP or UTP, you've got two different standards, and this is what I was referring to earlier. TIA/EIA 56A and 568B, 568A, 568B. It does not matter which one you use, as long as you're consistent. You should pick one and always use that one. Don't switch back and forth; it won't work. So the idea is that those colors on the cables that we saw go in very specific pins in your RJ45 connector. And as long as you're consistently using one standard or the other, you're going to be fine. So here's kind of a different view. Now, something that you may or may not be familiar with, our regular straight through cable is a cable that we're normally going to use in most situations. When we're hooking up our computer to, for example, a switch, we're going to use a regular straight through cable. It's going to terminate RJ45 plugs at both ends. They're going to look identical. There's going to be some situations occasionally that we want to be able to have a crossover cable. And this is going to allow us to hook up two nodes directly. And the advantage of this is we don't have to have a switch or anything like that. We can do some troubleshooting using crossover cables, and that's the idea behind it. As far as terminating twisted pair cables, some of the things that you're going to need: termination tools include wire cutters, wire strippers, crimping tools. And after making the cables, you need to verify that those cables are actually properly created. So as far as fiber optic cables are one or more. They usually either glass or plastic fibers in the center, and that's what actually carries the light pulses that reflect the data that represent the data that you're trying to transmit. The transmission themselves, pulsing light sent from a laser or LED through those central fibers. those signals are protected by the cladding. The cladding is what surrounds that fiber and allows it to, helps to protect it, helps to reflect the light back to the center core, which gives it more distance and allows that fiber to bend without breaking. So here's an example of the plastic buffer outside the cabling, some of the cladding and stuff like that inside, and then the individual fiber optic cables themselves. And another representation of that. So the benefits of fiber optic over cabling, well, the big one is throughput. Lots of data, very fast. It's also highly resistant to noise. So electromagnetic interference, for example, does not affect fiber optic cable. So if you're in an environment that has lots of machinery going, lots of motors, lots of electrical components that, and you're talking about mission critical systems, fiber optic may be a way to go. And it is extremely expensive. That's one of the drawbacks down here. So that's one of the bad things. It's also difficult to work with in terms of terminating it properly, splicing it, things like that. It's difficult to work with. But this particular drawback also is an advantage in the sense that because it's harder to splice, it makes it harder for people to try to tap into your line. So it provides for better security as well. Allows signals to go for longer distances and is pretty much the standard for high-speed networking. There's different kinds of fiber optic. There's single mode fibers, multimode fiber. We'll talk about multimode here in just a second. The single mode consists of narrow core, gives you a measurement there. I don't know that you really need to know the precise measurement. But as far as what actually generates the signal, usually either a laser or an LED, and it allows you to send data over a very long distance. In some cases, several miles without having to actually use any sort of a repeater. It's not used for shorter connections, so if you're talking about a LAN environment or something like that, it's not usually used. It's just too expensive to be able to justify that. Multimode fiber it is the same general concepts, but it is slightly different. You can see that it's larger in size, uses a laser or LED to generate those light pulses. It has greater attenuation than single mode fiber. In other words, it's not going to transmit quite as far as a single mode fiber because it has greater attenuation. Common uses: cables connecting a router to a switch, cables connecting the server to a network backbone. So you might see this in more of a server environment where you have a server connected to a backplane of disks, hard disks or something like that, in a SAN type of setup, where high speed is very important, but so you need that ability to transmit lots of data extremely fast. Fiber optic converters, we already kind of talked about this just a little bit, but required to connect multimode fiber networks to single mode fiber networks, as well as fiber to copper-based parts of the network. So you can convert back and forth, but you've got to have special hardware to be able to do that. Serial cables are another type of transmission medium that get used periodically. You don't see these as much anymore, but they are still used in some situations. Serial cables refer to how the data is going to be transmitted serially as opposed to in parallel fashion. The pulses are issued sequentially, not simultaneously. So we send our bits out one at a time, 1, 1, 1, 0, 1, 0, 0, 0, 1, 1, as opposed to several of those all at the same time. This is good for high speed. It's also good for when you have a transmission that's going to occur over a long distance and you can't run multiple lines. Serial transmission, the standard is RS-232, and you can see different types of connectors that use it. DB9, DB25, RJ45 connectors all use serial transmission. Now when we go to wire a facility, usually we're going to have there are some standards that tell us how these facilities should be wired up, at least best practices for how these facilities should be wired. And usually you're going to have some sort of a cable plant, and this is hardware that makes up the enterprise cabling system, where it's all going to come together and kind of be dispersed throughout that particular building. You can follow cabling standard, again, TIA/EIA's joint 568 commercial building wiring standard. they've created this standard. It's called structured cabling that basically kind of dictates what best practices are and how you should organize those cables for a particular building. And they really kind of take a hierarchical approach to it. So here we have an example of maybe 3 different buildings or 3 different floors of a particular building. We've got the point of demarcation where our network connection may be coming in from the outside. That may be an internet connection, it may be a connection back to headquarters, could be several different things. But it's going to come into an MDF, a main distribution frame. And from there we can distribute that to other floors or other buildings, to IDFs. And then from there, we can go even more local, closer to the individual areas that need to be wired into some sort of a wiring closet, telecommunications closet. And then from there, we can run our individual wires. So it takes that very hierarchical approach from the top down to smaller closets, smaller wiring distribution centers, ultimately to our individual nodes on the network. As far as some of the components, the entrance facilities, the MDFs, the cross-connect facilities, IDFs, backbone wiring, those telecommunications closets, horizontal wiring, things that may be held up in drop ceilings, and then ultimately the drops to the work areas where the nodes will actually connect. So kind of some examples of these different kinds of cabling that we've talked about and some of the characteristics, if you will. Unshielded twisted pair, the distances that we can look at, the cross connects to telecommunications closets, the MDF to IDF, the distances for these different types of cables to these different locations in our building. So again, if we're going to use fiber, we can see that our distances are much longer. So when we come into the building, all the way down to the closet, we can see some of those distances right there. So best practices for cable installation and management: choose the correct cabling. It's really going to depend on the needs and requirements of your facility. The vast majority of the time you're going to be talking about UTP or STP, usually UTP. But there are going to be situations where you're going to need to be able to use fiber or something else. Follow those TIA/EIA standards as far as the wire color coding and all that kind of stuff. As far as network problems, often traced to poor cable installation techniques. So if you're doing a bad job of routing your cables, you're running them near electrical lines, things like that. If you're terminating them poorly, you're going to have problems. You're going to create problems for yourself. Installation tips to prevent the physical layer failures. You can look at your text. I believe it's on page 121 to 122. They give you a lot more tips to help prevent some of those issues. So to summarize this chapter, we talked about different transmission methods. We talked about analog, we talked about digital. We talked about the advantages and disadvantages of both. We talked about multiplexing and the ability to use multiplexing when you have long distances between something and between 2 different sites that need to communicate with just a single transmission medium. Multiplexing allows you to have multiple devices connected to each other using that single medium. We talked about full and half duplex specifics and how signals can travel in one direction, both directions at the same time or not. We talked about how noise distorts both analog and digital signals and how to go about fixing those or extending the distance of both of those types of signals. We talked about attenuation and the loss of signal as it travels. We talked about some of the different types of cable. We talked about coax, for example, and the insulators and the shielding and stuff like that. We talked about shielded twisted pair and unshielded twisted pair. And we talked about fiber optic cable and some of the advantages and disadvantages of that. We finished up talking about serial communication and structured cabling. So that is chapter 3 in a nutshell. So hopefully you have a better understanding of some of the transmission basics and networking media. If you have any questions, send me a message. Follow me on Twitter at H.Schuessler PhD. Until next time, take care.